Hello and welcome to Linear Algebra, Chapter 3, Linear Mappings. So we finished our chapter on matrices. Now we're going to look at mappings, linear mappings. But first, we look in the general idea of what is a mapping. We're going to find in Chapter 3 that every matrix can be represented by a linear map, and vice versa. Every linear mapping can be represented by a matrix relative to a given basis. And so let us start Chapter 3, Section 1, Mappings. Now, the terminology for mappings is similar to the terminology for a function. We kind of use some fancy terminology that we afford to both mappings and just regular old functions. So let's start with two sets, S and S prime. All right, a mapping F going from set S into S prime is an association such that for every x in S, f of x is in S prime and it's unique. So that's the same definition as the definition for a function. Every x maps to only one y value. A function is a mapping from a set S into a field K. So this is where we distinguish between a mapping and a function. Mappings are more general than functions, and mappings are used in all disciplines in math. So a function is going into a field, and in our case, either the real numbers or the complex numbers. So if U is an element in set S, f of U is called the image of U under F. The image of F, denoted IMF, is simply the set of all images, f of U, where U is in S. And if W is a subset of S, then f of W is simply the set of all images, f of W, where W is in W. And it's the image of W under F. So notation, we can also write whenever X is in set S, X, and then the vertical bar with the arrow to f of X. Also denotes the image of X under F. Now, some more terminology I don't think was mentioned exactly there in the book. Of course, we call S the domain set, but now S prime is the codomain. And then f of S is the range or the image of F. And you note that the range is a subset of the codomain. Just a very simple example that we all know. If F is mapping from the real numbers to the real numbers by the good old parabola, f of x equal x squared, of course we know it's a function. And for example, g from the non-negative reals r plus to r by g of x equals square root x is a function, as we know. Look at example 3 coming up here. Example 3. All right, here S and S prime are the same set, and it denotes d infinity of 0, 1. It's the set of all functions that have derivatives of all orders. And I denote that by d infinity on the open interval 0, 1. So all functions that are differentiable on the open interval 0, 1 of all orders. Then the operation of taking the derivative, capital D equal d dt, is a mapping from d infinity into d infinity. In other words, d of f equals df. It's the operation of taking a derivative. So that the operation of taking a derivative is a function in itself. Okay? And let's look at example 4. Now, let S be the set of continuous functions on the closed interval 0, 1, and let S prime be the set of differentiable functions on the closed interval 0, 1. Now, define a mapping G going from the continuous functions to the differentiable functions by giving its value at any function f in the following manner. For every value x, let jf of x equal the integral from 0 to x of f of t dt. Then j of f is differentiable, and the derivative of j of f of x equals f of x. This is simply the second fundamental theorem of calculus that you learn about in Calc 1, which is probably not as memorable as the first fundamental theorem of calculus, but it's very important. You know, the derivative of the integral gives us the original function, is what it basically says, because differentiation and integration are inverse operations, aren't they? And then example 5, let S be R3, okay? And let A be an ordered triple, say 2, 3, negative 1. Let L be a mapping going from R3 into R, be given by L of x equals A dot product with x, where x is the ordered triple x, y, z. In other words, L of x dot product is the following: 2x plus 3y minus z. So that's a mapping. We're going to learn in the next section that it's an example of a linear mapping. Okay? Now I skipped example 6 and I'm going to do example 7. Look at example 7. Let f and g be mappings from set S into a vector space V over field K. Then the set, call it W, of all such functions f, or mappings, from S into V is a vector space with the following definitions of addition and scalar multiplication. Addition of functions is defined in the usual way, that is, element by element. F plus g of t equals f of t plus g of t for every t in S, and whenever c is a scalar, cf of t is c times f of t for all t in S. So that's the normal definition of adding functions and multiplying functions, or mappings rather, by scalars. Okay? Now, something that might be a little bit more new to you, example 8 is defining parametric curves. Look at example 8. Let S be a set, and let F be a mapping going from set S into the vector space Kn. Okay? Now, for every element T and S, f of T, the image of T, is a vector. Okay? It's a vector in Kn, but it can be defined by its coordinate functions, f sub 1, f sub 2, dot, 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 through f sub n, where capital F of T is the ordered n-tuple whose coordinates are f sub 1 of T, comma, f sub 2 of T, dot, 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 through f sub n of T. Now, if the set S is an interval of real numbers, and it goes from that interval, call it J, into Rn, then this is called a parametric curve in Rn. Now, you may have seen a few of these in Calculus 3, particularly from going from J into either R2 or R3, specifically R3. But other than that, you probably haven't seen much of them. But it's an important example, especially geometrically. Okay, so next, we're going to define the fact that functions that are defined by coordinate functions certainly make a vector space. Okay, so let's look next. So let f and g be two mappings going from set S into Kn, okay, where f of t is defined by its set of coordinate functions, f1, f2 through fn, and g of t is also defined by its set of coordinate functions, g1, g2 through g sub n. Then, adding functions that are defined by coordinate functions and multiplying such a function by a scalar are defined in the usual way, f of t plus g of t. So it's going to be coordinate-wise, f1 of t plus g1 of t, dot, 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 through fnt plus g sub nt, and similarly for scalar multiplications. Cf of t is c times f of t, or as an ordered n-tuple, cf1t through cfn of t for all t and s. So there's no mystery there. And with that definition of addition, scalar multiplication, then those specialized functions, parametric functions, form a vector space. And that's all that says. Okay, next, the main thing we're going to need next is composition mappings. Composition mappings. Of course, your first introduction to composition functions is in college algebra. So let's take three sets. Let U, V, and W be sets. Okay. Let capital F go from U to V and capital G go from V to W be mappings. Then we're defining the composition mapping. Okay? Okay. G circle F going from U to W is defined as G circle F of t is simply G evaluated at F of t for all t in U. That's what we teach in college algebra. And then as a note, we also will note that composition of functions is associative. If you have three functions or mappings, say f, g, and h, f goes from u to v, g goes from v to w, and h goes from w to s, then h composed with G and F is the same as H composed with G and then composed with F. And so it's associative, and that's important. Of course, that goes back to the analog with matrices, that matrix multiplication is also associative. All right, and there's a little proof of that in the book. It's just a matter of playing with the parentheses, which is not very interesting, so I omitted it. The next important thing we need is the definition of an inverse of a map. But before we get to an inverse, we need to know what it means for a mapping to be injective, or one-to-one is the word we use in college algebra. So let's look next at the following definition. Let F go from set S into the set S prime, be a mapping. The map F is injective, or one-to-one, if whenever x and y are elements in S with x not equal to y, then f of x is not equal to f of y. Or what we normally use is the contrapositive of that definition, namely, a map F is one-to-one, or injective, whenever f of x equal f of y implies that x equals y. Now, an easy example from algebra is the good old parabola, f of x equals x squared from R to R. And it's not one-to-one when it goes from R to R. So let's see. Let's look at f of x equal f of y. So that means that x squared equals y squared, or square root both sides. X equals plus or minus y, or y equals plus or minus x. And so every y is mapping back to two x's, that which violates the definition of one-to-one, of a function or mapping being one-to-one. And so it's not one-to-one. And so again, that's something you should remember. And this is also covered in the Bridge to Higher Math, Math 3040. Okay, and so the next definition is surjective, or onto. Surjective or onto. So what does it mean for a mapping to be surjective? Okay, a map F from set S to S prime is surjective, or onto S prime, if f of S is equal to S prime. Okay? So what does that mean? It means for every y in S prime, there exists an x in S with f of x equal y. That's how you break that down. Okay? Now, let's see an example. Again, the good old parabola, x squared. Well, if you look at x squared from the reals to the reals, it's not onto the reals, is it? However, but if you restrict f from going to the reals to the non-negative reals, r plus, then it is onto, isn't it? Because we see that it goes to the non-negative real numbers. So sometimes one-to-one and onto depends on the restriction of the domain or the codomain. One-to-oneness can depend on the restriction of the domain, and onto, or surjective, can depend on the restriction on the codomain. And then finally, a mapping F is bijective if it's both injective and surjective. Okay? And then, of course, a standard notation for the identity mapping, I, from S to S, the identity mapping goes from the same set to the same set. Normally denoted by I sub S is the mapping I sub S of X equal X for all X in S. Sometimes you might see the notation little lowercase id or id also used for the identity mapping. Now that we have surjective and injective, we can now look at the definition of what does it mean for a mapping to have an inverse mapping. Okay, what does it mean? Let F go from S to S prime, be a map. Okay, F has an inverse mapping if there exists a mapping G going from S prime to S. So you're reversing the domain and codomain. So that two things are true. G composed with F is the identity map on S, and vice versa. F composed with G is the identity map on S prime. Okay? All right, so those are the definitions. So when does a mapping have an inverse? When does a mapping have an inverse? Look on page 50 in our textbook. Now, it's not completely labeled as a theorem, but it is a theorem for which you are responsible for the proof. Page 50, theorem. A mapping F going from set S to set S prime has an inverse map if and only if F is bijective. That is both one-to-one and onto. Now you probably remember that an if and only if theorem has two parts to its proof. The forward part and the reverse, the converse part. So the forward direction and then the converse direction. So proving the forward direction, suppose F has an inverse, call it G, from S prime to set S. So we got to show two things, right? We got to show that F is one-to-one and onto. One-to-one. All right? If F of X equals F of Y, then we got to show that X is equal to Y, and we do that using the inverse. Okay? So G is the inverse of F, so that means G composed with F of an element X or Y is equal to that same element. So X equals G of F of X equals G of F of Y, because F of X equals F of Y. But that's equal to Y, so that immediately proves that F is one-to-one, okay, or injective. Now, we want to show that F is surjective or onto S prime. So let Z be an element in S prime. We probably could have used the letter Y. We're more familiar with that. But let Z be an S prime. So you've got to find an X in S, right? So that F of X equals Z, okay? Well, we know now that with Z being in S prime means that the image G of Z is in S, so let's just give it a name. Let's let the letter X equal or represent G of Z, okay? Now let's apply the function f to that equation. F of X equals F of G of Z equals Z, because F and G are inverses. So we see then that F is surjective or onto S prime, hence F is bijective. And then the converse direction, suppose F is bijective, and then you want to show F has an inverse map. Okay. So we want to find an inverse map, G, going from S prime to S. And so the logical place to start would be in the set S prime. So let Z be an element in S prime. Since F is surjective or onto, there exists an element X in S with F of X equal Z, right? Since F is injective or one-to-one, this element X is unique. There's not but one of them. So we can define a function G from S prime to S by G of Z equal X. Then we have the two conditions for G being the inverse of F. We have number one, F of G of Z is equal to Z, and number two, G of F of X equals X. So we have both conditions satisfied. Hence, G is the inverse of F. And that concludes our video for section 3.1.